Today, we delve into a core challenge of computer science that underpins many of the most important algorithms we study and use in programming. Databases, web searches, pathfinding in games, and file systems on our computers all rely on the need to efficiently search, sometimes across vast datasets, to make information accessible, reliable, and useful. To understand how we might handle such problems computationally, let's first think about how we'd perform a manual search. Suppose we wanted to find our favourite book of poems in a public library. We could start in the poetry section, pick out a book, and if it's not what we want, we return it to the shelf and try again. With this random approach, we might get lucky, or we might continue to choose the wrong books over and over again. A better systematic approach would be to start at the beginning and check each book one by one. This is a linear search. We're guaranteed to find the book eventually, assuming it's there, but in a large collection, it could take a very long time. But library sections, by convention, are organised alphabetically by the author's last name. So, rather than starting at the beginning and checking each book one by one, let's go straight to the middle of the section. If our author's last name comes later in the alphabet, we can ignore all books before this midpoint. If it comes earlier, we can ignore all those after it. We repeat this process, going to the midpoint of whichever half remains and checking again whether our author is alphabetically left or right of that point. With each step, we cut our search space in half, quickly zeroing in on our book, even if the collection is enormous. This approach is the binary search algorithm. We can apply the same principles in programming. Imagine we have a large array of integers sorted in ascending order, and we want to search for the value of 30. As with our library example, we first check the midpoint. If it is greater than 30, we can ignore the right half of the array. If it is less than 30, we discard the left half. We repeat this process until we find our target. With a dataset of 100 values, binary search guarantees that we'll find our target if it exists within 6 steps. But if we double that dataset to 200 values, we only need one additional step. Each time the size of our set doubles, it takes just one more step to complete the search. With binary search, even as datasets get very large, the time required to search them grows very slowly. Let's consider how to implement binary search in Python. We'll define a function called binary search that takes 2 arguments, a list of integers sorted in ascending order and the target value we're searching for. To keep track of which part of the list we're searching for, we'll create variables to represent left and right indices of our search range. We'll initialize the left index to 0 and the right index to the final index in the list, which is 1 less than the length of the sequence. We'll perform the search within a while loop. This will continue as long as the left index is not greater than the right index. Within each iteration, we'll find the approximate midpoint of the current search range. To do this, we'll find the index that is midway between the current left and right indices, adding together the left and right indices and then dividing the sum by 2 using the floor division operator to ensure we get an integer. Next, we'll use an if statement to check whether the element at the center index of the sequence matches the search target. If it does, we'll return the center index, indicating the position where the target was found. Using elif, we'll check whether the element at the center index is less than the search target. If so, it means the target was not in the left half, so we can reduce the search space by setting the left index to the current center index plus 1. Otherwise, the element at the center index must be greater than the search target. Therefore, using else, we'll set the right index to the current center index minus 1. If we exit the loop without having found the target, it means the target value is not in the list. Therefore, we return false to indicate the search was unsuccessful. We'll test this in a new main function by searching through a sequence of randomly generated integers. At the top of the script, we'll import the random module. Using random.sample, we can create a list of random integers of any specified length within a defined range. For this example, we'll generate a list consisting of values between 0 and 10 million, with a length of 1 million elements. We'll sort the sequence in place by calling its sort method. To see the results of our binary search function, we'll use print to search the sequence we've just created for the value of 30. Running the program displays the outcome of our search, either the index where the value was found or an indication that it wasn't in the list. Our binary search function takes an iterative approach, repeatedly looping and dividing the problem in half with each iteration. We could instead adopt a recursive approach, where the function calls itself to search a smaller portion of the list each time. Let's also explore how to implement this version. As before, our function will take a sequence to search and the target we're looking for. This time, however, we need to specify the indices that mark the start and end of the current search range. Inside the function, we'll find the approximate center index by dividing the sum of the start and end indices by 2 using the floor division operator. We'll check if the start index is greater than the end index, and if so, return false to indicate we've searched the entire list without finding the target. With elif, we'll check whether the element at the center index of sequence matches the search target. When it does, we'll return the center index, which represents the position of the target within the list. Using another elif statement, we'll check whether the current midpoint is less than the target value. In this case, we'll return the result of calling the binary search function, narrowing down the search range by using the center index plus 1 as the new start index while keeping the end index unchanged. The final else statement will handle cases where the value at the midpoint is found to be greater than the target. We'll narrow our search range again by returning the results of binary search with start index unchanged and center index minus 1 as the new end index. As before, in main we'll use print to display the results of searching a randomly generated sequence for the value of 30. We'll specify an initial start index of 0 and a final index equivalent to the length of the sequence, so we're beginning the search with the entire sequence. We'll run the program to see the results of our search printed to the screen. Both iterative and recursive versions of our function work well, but there is one crucial inefficiency in this program. Each time we run it, we generate a random sequence of integers and then sort it. But sorting has a much higher time complexity than searching, even compared to a linear search. It would therefore be faster just to search the unsorted list linearly in this situation. Binary search works best when we're likely to search the same dataset repeatedly. This underscores a key point about algorithms. Effectiveness depends entirely on context. More important than learning how an algorithm works is understanding when and why to use it. I hope you found this helpful. Leave your feedback, thoughts, and suggestions in the comment section below. Please like and subscribe, and thank you for watching.